We're about to embark on a journey through the birthplaces and graveyards of stars. These are the nebulas, vast clouds of gas and dust scattered across the cosmos, some glowing with the light of 1,000 suns, others so dark they swallow entire galaxies from view. We won't be looking at them from a distance. We'll be drifting through them, across structures that span trillions of kilometers, witnessing the forces that create and destroy entire solar systems. Let's begin. The word nebula comes from the Latin for cloud, and that's exactly what we're seeing as we approach the Orion Nebula, 1,344 light-years from Earth. But this is no ordinary cloud. We're looking at a structure 24 light-years across, so massive that if we could stand at one edge, light itself would take 24 years to reach the other side. These clouds are made primarily of hydrogen and helium, mixed with heavier elements like carbon, oxygen, and iron, ejected from previous generations of stars. In a very real sense, nebulas are both the remnants of stellar death and the seeds of future worlds. As we drift closer to Orion, notice how the darkness begins to glow. We're not seeing reflected light, we're witnessing fluorescence. Ultraviolet radiation from newborn stars is energizing the hydrogen gas around us, causing it to emit that distinctive red-pink hue at a wavelength of 656 nanometers. This is H-alpha emission, the signature of hydrogen atoms losing and regaining electrons thousands of times per second. We're entering a three-dimensional structure now, not a flat photograph. If we could see this with our own eyes instead of through long-exposure cameras, it would appear as a faint, ghostly green glow, barely visible against the star field. But we have the advantage of collected light, months of photons gathered and enhanced, revealing the nebula in all its intricate detail. We're now approaching the heart of the Orion Nebula, a region called the Trapezium, named for the 4 brilliant stars at its core. These stars are monsters based on their observable characteristics. The largest is 40 times more massive than our Sun and burns at a surface temperature of 40,000 Kelvin, compared to our Sun's relatively cool 5,800 Kelvin. The process that created these giants is happening all around us. We're floating through a stellar nursery, where gravity is slowly winning a battle against the outward pressure of gas. In dense pockets throughout this cloud, hydrogen is collapsing inward. When these pockets reach about 10 million Kelvin at their cores, something remarkable happens. A star ignites. Look closely at the structures around the trapezium stars. Those teardrop shapes, glowing at the edges, are called proplyds, protoplanetary disks. Each one is a solar system in formation. The disk we're observing now is about 500 astronomical units across, 500 times the distance from Earth to the Sun. Inside that disk, dust grains are colliding, sticking together, slowly building the rocky cores that will one day become planets. We're witnessing planetary formation in action. The violence of star birth creates the conditions for planetary systems to develop. The radiation pressure, the stellar winds, they sculpt and compress the surrounding material, triggering new generations of collapse. Notice the colors deepening around us, the pinks intensifying into magentas, violets appearing in the densest regions. Each color represents a different element being excited by stellar radiation. Hydrogen glowing red, oxygen shining blue-green, sulfur adding golden yellows. We're seeing the periodic table painted across space in wavelengths of light. We're now 7,000 light-years from Earth, approaching one of the most famous structures in the cosmos, the Pillars of Creation in the Eagle Nebula. As we approach, the scale becomes almost incomprehensible. The tallest pillar stretches 4 light-years from base to tip, nearly the distance from our Sun to the nearest star, Proxima Centauri. These aren't just clouds, they're monuments sculpted by starlight. The process is called photoevaporation. Massive young stars located just outside our view are bombarding these pillars with intense ultraviolet radiation, heating the surface gas to thousands of degrees and blasting it away into space. But the pillars survive because within them, dense knots of gas and dust are shielded, creating shadows in the stellar wind. If we could stand at the base of one of these pillars and look up, we'd be staring at a column of gas rising 37 trillion kilometers into space. For perspective, that's 250,000 times the distance from Earth to the Sun. Its edges glowing emerald and gold as oxygen and sulfur atoms fluoresce in the ultraviolet bath. Now watch what happens when we switch our vision from visible light to infrared. The opaque dust that made the pillars look solid suddenly becomes transparent. Inside, hundreds, thousands of stars appear, still wrapped in the cocoons of gas from which they formed. Some are actively feeding, pulling in material from the surrounding cloud, growing larger with each passing century. The pillars are both cradle and crucible. Stars are being born inside them even as the radiation from their older siblings slowly erodes the structure. What we're witnessing is a moment frozen in cosmic time, a cathedral of gas that exists only briefly on astronomical timescales. Not all nebulas announce themselves with light. We're now approaching a different kind of structure, one that reveals itself only by what it hides. This is the Horsehead Nebula, part of a vast complex of dark molecular clouds in the constellation Orion. The Horsehead is a pillar of dense gas and dust. The cloud contains enough material to create hundreds of solar systems, but unlike the pillars of creation, there are no nearby stars to illuminate it from within. We see it in silhouette, blocking the red glow of hydrogen gas behind it. Temperatures are near absolute zero, around 10 to 20 Kelvin, cold enough that molecules freeze onto dust grains. These dark nebulas are the coldest, densest places in the galaxy. Inside Barnard 68, a dark globule we're passing now, the density reaches 40,000 particles per cubic centimeter. Earth's atmosphere at sea level has about 10 billion particles per cubic centimeter. But in the near vacuum of space, this is remarkably dense. So dense, in fact, that visible light cannot penetrate it. If we positioned ourselves behind Barnard 68, we'd see nothing. Absolute darkness, as if a hole had been cut in the fabric of stars. But darkness doesn't mean lifeless. These clouds are chemical factories. Complex molecules can form: water, ice, carbon monoxide, methane, even organic compounds like formaldehyde and ethanol. The shadows we're drifting through are latent with potential. Given enough time, the cloud will fragment and collapse. New stars will ignite, transforming this silent, frozen darkness into a brilliant nursery like Orion. The cycle continues. Not all stars die gently. We're now approaching the Crab Nebula, 6,500 light-years from Earth. And what we're seeing is the aftermath of catastrophic violence, a supernova explosion witnessed by astronomers in the year 1054. For 23 days, this stellar detonation burned brighter than Venus in Earth's daytime sky. Unlike the planetary nebulas, this is a star that was torn apart in seconds. When a massive star, one at least 8 times more massive than our Sun, exhausts its nuclear fuel, there's no gentle puffing of outer layers. Instead, the core collapses in less than a second, from a sphere the size of Earth to a ball just 20 kilometers across. The implosion rebounds in a shockwave traveling at 30,000 kilometers per second, 10% the speed of light, blasting the star's outer layers into space with the energy of 100 billion suns. We're now drifting through the debris field. The Crab Nebula spans 11 light-years, and is still expanding outward at 1,500 kilometers per second. The filaments we see, those delicate, thread-like structures in red and orange, are the shredded remnants of the star's atmosphere. Spectroscopic analysis reveals iron, calcium, nickel, and dozens of other heavy elements being scattered into space. The gentle deaths of sun-like stars can only create elements up to carbon and oxygen. But supernovas forge heavier ones like gold, uranium, and iodine. At the center of this chaos sits something extraordinary: a neutron star, the collapsed core of the original star. It's only 25 kilometers in diameter, but contains 1.4 times the mass of our entire Sun. A teaspoon of neutron star material would weigh 4 billion tons on Earth. This object is spinning 30 times per second, and with each rotation, it sweeps beams of radiation across space like a cosmic lighthouse. We call it a pulsar. The pulsar is the engine driving the nebula's glow. It's generating a magnetic field 1 trillion times stronger than Earth's, accelerating electrons to nearly the speed of light. These electrons spiral through the magnetic field, producing the eerie blue-white synchrotron radiation that permeates the nebula's interior. Look at the structure carefully. See those knots and tangles in the filaments? Each one marks a place where the supernova shockwave has slammed into slower-moving material. The collision heats the gas to millions of degrees. The Crab Nebula is still evolving, raw, explosive power that fundamentally transforms. Now we drift towards stellar death. This is the Helix Nebula, 650 light-years away. Often called the Eye of God for its haunting resemblance to a cosmic pupil staring back at us. At the center burns a white dwarf, the collapsed core of a star that was once similar to our Sun, maintaining equilibrium between the inward crush of gravity and the outward pressure of nuclear fusion. But when the hydrogen ran out, the outer layers, no longer supported, expanded outward, swelling the star into a red giant hundreds of times its original diameter. Then, in the star's final act, it expelled those outer layers in a series of pulses, each one ejecting a shell of gas traveling at 20 to 30 kilometers per second. What we're seeing now is the aftermath, those shells expanding outward, glowing as they're ionized by ultraviolet radiation from the white dwarf core, which burns at a scorching 120,000 Kelvin. The helix is 2.5 light-years across and still expanding. Within it, the gas glows in electric blues and cyans, doubly ionized oxygen, mixed with neon oranges and reds from hydrogen and nitrogen. The symmetry is remarkable, almost artificial-looking, created by the star's rotation and magnetic fields shaping the outflow. Now we turn toward the Butterfly Nebula, 3,800 light-years distant. Here, the dying star's ejection wasn't spherical, but bipolar, two lobes of gas blasting outward in opposite directions at speeds exceeding 600 kilometers per second, faster than almost any other planetary nebula known. The reason lies in the star's equator. A dense disk of gas and dust channeled the dying star's final exhalations into two focused jets. The result is one of the most spectacular structures in the sky. Wings of gas span 3 light-years, glowing in brilliant reds and blues. The central star, hidden behind thick dust, is one of the hottest known, possibly exceeding 200,000 Kelvin. We're witnessing a brief, brilliant finale, the last light show of a star's existence. Our journey through the nebulas ends here, but their story continues. Right now, across the observable universe, millions of stars are being born in clouds like Orion. Millions more are breathing their last, creating new planetary nebulas. Thank you for joining the journey. Subscribe to see where and when we travel next.